An aquarium is to be built out of glass. It will have a rectangular base and rectangular sides. There will be no top. The length of the base will be twice its width. The volume is to be 36 cubic feet. Our job is to find the dimensions of the aquarium that minimize the amount of glass needed to build it. Now, in problems like this, the first thing you should do is draw a picture. And the picture here is pretty easy. We've got a rectangular solid here. That's the base. There are the heights, and there's not going to be a top. The next thing to do is to choose appropriate variables to label the diagram. Now, in this particular problem, you'll notice that the length of the base is supposed to be twice its width. So what we do is the width we label with x, and that means the length of the base is going to be 2x. We'll need another variable for the height, which we'll take to be y. The next step is to use the diagram to obtain equations for the objective function and the constraint. Okay, the objective function is the thing we're trying to either maximize or minimize, and here we're trying to minimize the amount of glass used, so we need an equation for the amount of glass, and that comes from the base is x times 2x, so the glass that we're using for the base is 2x squared. This front face has length 2x, height y, so the area of that rectangle is 2xy. There's a back face as well, and that's why we have two of them. The side is x times y. We've got two of those, and that gives us our 2xy. Do some algebra. We've got 2x squared plus 6xy. Now the constraint is the volume has to be 36 cubic feet. So V equals 2x squared times y, and that's 2x times x times y, and that's got to be 36. Okay, next step is to use the constraint to solve for one of the variables, and we get that y is 36 over 2x squared, or 18 over x squared. We do this so that we can plug into the objective function to get a function of one variable, which we do 2x squared times 6x times 18 over x squared, which we simplify to 2x squared plus 108 over x. Now the next thing to do is to find the domain of this objective function. These are the values of x that make any sense in the problem. And pretty clearly x can't be negative, but it also can't be 0, because then we would have an aquarium of volume 0, which is not 36. But pretty much any positive x will allow us to make an aquarium with the right volume by making this choice for y. So that our domain is actually 0, infinity. Now the next thing to do is to find the critical points in the domain of the function. And we do this by taking the derivative of the objective function, which gives us 4x minus 108 over x squared. And that's because the derivative of 1 over x, which is x to the minus 1, is minus x to the minus 2. Okay, we're going to set that equal to 0. We do some algebra and get 4x cubed is 108, which turns into x cubed equals 27, which is x equals 3. Next, what we want to do is check possible values and see which of them, if any, is the global minimum. And here, 3 is the only possible choice, as there are no endpoints. However, it's a unique critical point. So if it's a local minimum, it is the global minimum. And we can test that using either the first or second derivative test. Here we're going to use the second derivative test. We calculate g double prime, which is 4 plus 216 over x cubed. And the reason is that the derivative of x to the minus 2 is minus 2x to the minus 3, which is how we get to here. And the question is that positive or negative? It is in fact positive for x equals 3. And that means we're concave up, which means we've got a local minimum, which means it's the global minimum. The next step is just to find what the dimensions are. And we know x is 3, which means that the long side of the base is 2x, or 6, and the height is y equals 18 over x squared, which is 18 over 9, or 2. And that gives us a 6 by 3 by 2 aquarium.